back. So we were trying to prove this particular theorem. If limit x approaches a of fx is L and limit x approaching a of gx is M, if both these limits exist, then limit x approaching a of fx plus gx, the function, the sum of these two functions is sum of the limits. Okay, so I hope you have had some time to think about this. Here is the proof. Limit x approaching a of fx is L. So we are told that this limit exists as a real number, and limit x approaching a of gx is M. We are told this number exists. So what does that mean? These two limits exist, and that's the limit for f, that's the limit for M. Then given any epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than absolute value x minus a less than delta, that is x is within delta distance of a, then fx is within a small distance of L. So you see, given any epsilon, I can find a delta. Here I have found a delta for epsilon over 2. Why not? For any epsilon, I can find a delta. In particular, I took half of what you gave me and found a delta for it. Okay? You gave me some. So that's what given means. You gave me an epsilon. I used half of it for f and found a delta. Likewise, I used the other half for g and found a delta. Aha. You may ask, why the same delta? Well, in theory, I could have found a one delta and another delta here, right? But why not take minimum of the two deltas? If I take minimum of the two, then I am very much within the required distance. That's why I'm using the same delta. Okay, if you like, I can say let delta itself be minimum of delta 1 and delta 2. So if I choose the minimum of the two, then I can combine these two sentences in one go. If distance between x and a is less than delta, right, which is minimum of these two, then both of these conditions hold true. Both of these conclusions hold true. Then this is less than epsilon, this epsilon over 2, and this is less than epsilon over 2. So their sum is less than epsilon over 2, epsilon over 2. You see? In other words, I found a delta such that if the distance between x and a is less than delta, then absolute value fx minus L plus absolute value gx minus M, it should be M, is less than epsilon. Okay, epsilon by 2 is epsilon. Now, let's understand this. You see, I don't want this. This seems to be broken up absolute values. I want one combined absolute value. Absolute value fx plus gx minus L plus M is nothing but absolute value fx minus L plus gx minus M. So notice plus gx. Now, what does this mean? It's still within one absolute value. You see, if I have two numbers with an absolute value, it's actually less than or equal to absolute value of each number. Check for yourself. What am I saying here? This is called triangle inequality. Okay? Check for yourself. So, a small check. If I take absolute value of 5 plus 8, okay, is it less equals absolute value 5 plus absolute value 8? Yes. Okay, So when I split the absolute value, do I have less than or equal to? You might say, why should I have less or equals? It should be equal. Well, in this case, it is equal, but let's try the following. Absolute value 5 plus negative 8. Question is it less equals absolute value 5 plus absolute value negative 8? Well, 5 plus negative 8 inside absolute value is negative 3. And the right hand side gives me positive 13. That's why you have less or equal. You want to consider the possibility of negative numbers inside. Okay, so you're not guaranteed absolute value of a sum to be equal as sum of absolute values. It's actually less equals. Okay, so that's the result I'm using here. This is, by the way, called triangle inequality. Anyway, so absolute value of sum of two things is less equal sum of the two absolute values. But sum of the two absolute values we already saw was less than epsilon. In other words, absolute value fx plus gx minus L plus m is smaller than epsilon. Okay, so that's that. If x is within delta distance of a, then fx plus gx is within epsilon distance of L plus m. This is what it means to say limit x approaching a fx plus gx is L plus m. All right. So this is what is called a proof. You start with a few given assumptions and you give me the final conclusion. You start with hypothesis and you have proved the conclusion. That's a proof. All right. Continuing, infinite limits. Infinite limits can also be defined in a precise way. Precise definition of an infinite limit. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. F may not be defined at a. If it's defined at a, fine, but it may not be defined at a. Then limit x approaching a of fx is infinity means that for every positive number m, there is a positive number delta such that if distance between x and a is less than delta, then the value fx is greater than m. Look, I'm going to positive infinity. So you give me however big a number m, if I get close enough to a, then fx can cross the given big number m. That is, fx can be larger. All right. So this is the meaning of infinite limit. Your f is not bounded by any m. You gave me some number m and I'm able to cross it. All right. If I'm close enough to a, I'm able to cross that bound. All right. This says that the values of fx can be made arbitrarily large. Arbitrarily large, that is larger than any given number m, by requiring x to be close enough to a. So that's your a. You gave me an m and that's my function f, okay, graph of mine. So if x is close enough to a, then fx, look at the two branches, they have crossed the number m you gave us. All right. If x is close enough to a, that is within distance delta, where my delta depends on m. So if you had given m even higher, my delta would have become even smaller in this particular case. So this is the geometric interpretation. Okay. Given any horizontal line y equals m, we can find a number delta greater than 0 such that if we restrict x to the interval a minus delta to a plus delta, that is, x is from a going to the left at most a minus delta but not equal, that's why this is an open interval. Likewise, on the right, x can go as far as a plus delta but not equal a plus delta. So as long as x lives in this interval but x is not a, like in this case, at a, f is not defined. Okay, so we don't want x to be a, then the curve fx lies above the line. That's what it means to have crossed the number m. Your function f is even higher valued than m when x is close enough to a. So that's what this means. Okay, given any horizontal line y equals m, we can find a number delta greater than 0 such that if we restrict x to lie in this interval a minus delta, a plus delta, but x is not a, then the curve y equals fx lies above the line y equals m. You can see that if a larger m is chosen, then a smaller delta may be required. Use this definition to prove limit x approaching 0, 1 over x squared is infinity. Let m be any given positive number, any given positive number. We want to find a delta such that if x is within delta distance of 0, x not equal to 0, then my function value is greater than the number you gave me. All right. So let's understand this. This will help us to find a delta. 1 over x squared greater than m is equivalent to saying, cross multiply and so on, x squared is less than 1 by m, which is equivalent to saying take square roots. Look, my x is positive, m is positive, so a square root of x squared, x need not be positive because x is approaching 0, could be approaching from the left. So square root of x squared is absolute value x. On the right hand side, I have 1 over square root m. Now, that's what we will choose to be our delta. Absolute value x less than delta means will imply 1 over x squared greater than m. That is 1 over x squared approaches infinity as x approaches 0. On the other hand, negative infinity, it's a similar definition. Let f be a function defined on some open interval that contains the number a except possibly a itself. Then limit x approaching a of fx is negative infinity means that for every negative number n, take any negative number n, there is a positive delta such that if distance between x and a is less than delta and x not equal to a, that's what this phrase represents, then fx is less than negative. Notice I'm going to negative infinity. So you give me any negative number, my fx can go below it. That's what this definition says. All right, so this completes our theory for section 1.7. Next videos will cover problems on this section. Until then, bye.